For the first time in history, hurricanes are now so powerful that they cannot be described by our standard scales of measurement.
This is a buzzsaw.
We're looking at a life-threatening situation.
A really deadly hurricane.
I've not seen anything like this. It's a record breaker.
The fastest a hurricane has ever intensified.
This era of superstorms was started by the deadly typhoon Haiyan in 2013, and followed 2 years later by the 215 mile per hour Hurricane Patricia. The most extreme storms in recorded history seem to be getting more extreme. What initially interested me when I saw the reporting on this was how can we have a storm that is so powerful that we can no longer measure it on our scales? What does that actually mean? And how sure are we that we understand what exactly is driving this increase in power? And I guess ultimately, just how bad are things going to get? Before I get started, let's talk about definitions, because I'm already using some US-centric terminology here of hurricane, but I could also say cyclone or typhoon, ultimately meaning just a very powerful storm condition with high wind speeds. But not a tropical storm, to be clear, because that is a related but less powerful version with wind speeds of 39 to 73 miles per hour. Or a tropical depression, which is a wind speed below 39 miles per hour and was named as it kept on ruining holiday goers' vibes. Hurricanes have wind speeds above 74 miles per hour, unless you're in the Indian Ocean or the South Pacific Ocean, west of 160 degrees east, where it's now called a tropical cyclone, or you're in the Northwest Pacific Ocean, where it's now called a typhoon. That means that weird things can happen, like when Hurricane Genevieve became Super Typhoon Genevieve, its Super Saiyan alter ego as it crossed from east to west over the international dateline. Today, I'm going to be using the words interchangeably, probably sticking to hurricane and using miles per hour as a result. Don't at me because that's the one I've gone with. Hurricanes are ranked based on their intensity by the Saffir-Simpson Hurricane Wind Scale, developed by Robert Simpson and Herbert Saffir. Simpson in particular had a personal history with devastation of large storm systems. In 1919, when Simpson was 6 years old, a particularly devastating storm hit Corpus Christi, Texas.
100 years since the deadliest hurricane in the history of the coastal bend.
Officially, 284 people died, but the real number is likely to be much higher,
causing storm surge of up to 16 feet that led to widespread flooding and damage and an estimated death toll ranging from 600 to 900 people. Where many of those victims were swept out and lost at sea. The experience left Simpson with a lifelong fascination of the weather, especially with hurricanes. Following his physics degree, he was eventually hired as a meteorologist in 1940. He repeatedly sought funding for hurricane research, but it was denied due to the limited Weather Bureau budgets of the time. However, in 1954, a catastrophic hurricane season caused $750 million in damages and took the lives of over 1,000 people, changing everything. The research team that was assembled to improve the understanding and forecasting of these powerful storm systems believed a key piece of data they were missing was direct observation. Collecting real-time data from inside hurricanes, the Hurricane Hunter missions that were assembled led flights into the heart of hurricanes to gather this critical information, of which Simpson was an eager participant in many of the early flights. Simpson's main contribution, however, came once the science began to be understood, and meteorologists had a measure of success in predicting their paths. The next step was how to communicate this information to the public. Together with Herbert Saffir, Simpson worked on a simple scale to describe the probable damage from hurricanes across 5 categories of increasing wind speed and damage potential. Category 1 hurricanes began with speeds above 74 miles an hour and up to 96 miles an hour, and were capable of causing minimal damage primarily to unsecured homes with potential for minor flooding. At Category 2, with wind speeds of 96 to 110 miles an hour, some damage to roofs, windows, and doors was expected, with considerable damage to vegetation, mobile homes, and piers, including coastal and low-lying escape routes being flooded 2 to 4 hours prior to the arrival of the hurricane center. At Category 3, which is classified as a major storm, wind speeds were in excess of 111 to 219 miles per hour. Some structural damage to small residences and utility buildings was expected, with large trees being blown down, and coastal and low-lying escape routes now being flooded 3 to 5 hours before the arrival of the hurricane center. At Category 4, wind speeds of 130 to 156 miles an hour, roof structure failures on small residences was expected, with major erosion of beach areas and major damage to lower floors of structures near the shoreline. But Category 5 is the one that we're interested in, with wind speeds in excess of 157 miles an hour, capable of laying devastation to a high percentage of framed homes, with total roof failures and wall collapse, with trees and power lines downed and power outages that may last for weeks to months, making these areas uninhabitable during the reconstruction period. Now, this scale has been an effective and a simple way to communicate risk to the public. That is, up until about the last 10 years or so, when that already devastating description of a Category 5 storm has started to no longer be adequate to reflect the damage that a weather system is capable of delivering. We saw the first evidence of this in 2015, just 1 year after Robert Simpson passed away. Hurricane Patricia formed near Mexico. Initially only growing comparatively slowly, conditions lined up to create the perfect storm on October 22nd, accelerating its speed by a record 120 miles per hour in a single day, and then peaking further a day later with sustained wind speeds of an astonishing 215 miles per hour, the fastest hurricane ever recorded. Fortunately, though, despite its intensity, Patricia caused significantly less damage than expected due to its relatively small size and the fact that it made landfall near a mountainous region, which disrupted the hurricane's structure, rapidly weakening it. It also landed on a largely underpopulated area that was almost fully evacuated. But even in its weakened, short-lived form, it caused $325 million in damages and resulted in 6 deaths. This was the first warning shot that more powerful storms than we had ever seen before were coming. And you might be saying, hang on, Category 5 says winds above 157 miles per hour, so that's just a big Category 5 storm. And if it's that devastating, why does it matter to further delineate it? Well, let's look at the simple physics behind this to understand and put it in perspective. The Saffir-Simpson scale measures wind speed, which is fine but doesn't necessarily give you an understanding of just how much more destructive these storms can be. Let's borrow some maths from wind turbines to talk about it. Adapted from the kinetic energy formula, the power over a given area available in the wind is related to the cube of the wind speed. So just in case you're thinking about the damage that wind can do at different wind speeds as a linear relationship, it's actually something that looks more like this. The initial categories increase in number roughly every 50 to 80% power increase between the categories. The jump from 157 miles per hour at the low end of Cat 5 to 215 miles per hour of Hurricane Patricia is a 150% increase, delivering roughly 2.5 times the destructive power. That wind speed is also what drives another major destructive force, which is coastal flooding. Hurricanes form over warm ocean waters, typically when the sea surface temperature is at least 26.5 degrees Celsius or 79.7 degrees Fahrenheit. The warm water heats the air above it, causing the air to become less dense and rise. This creates a pressure gradient force, with higher pressure outside the storm moving air towards lower pressure at the center of the storm. The Earth's rotation causes this inward moving air to spiral due to the Coriolis effect, creating the hurricane's characteristic spinning motion. The intense low pressure at the center of a hurricane causes the ocean's surface to rise temporarily. Combining this with the hurricane's strong winds pushing water towards the coast, this creates a storm surge, which can lead to significant coastal flooding and heavy rainfall up to 100 to 200 miles inland. Hurricane Katrina, which struck the Gulf Coast of the United States in late August of 2005, caused catastrophic flooding in the city of New Orleans, Louisiana, which combined with destroying levees in the area left 80% of New Orleans underwater, with water levels in some areas reaching 20 feet or 6 meters deep. 800,000 housing units were destroyed or damaged in the storm, and Katrina remains the costliest US hurricane, with the economic damages estimated at $125 billion. Katrina was a Category 5 storm, dropping to a Category 3 storm as it made landfall. Katrina's maximum wind speed was 175 miles per hour. Patricia's wind speed was 215. the destructive potential is significantly higher. If this was a freak storm, that's one thing. But if these freak storms are starting to occur more and more often, then the scale that we work with can no longer describe our 21st century weather. At least that's the conclusions of Michael Werner and James Cossin of the University of Wisconsin-Madison and the Lawrence Berkeley National Laboratory, respectively. In their publication in the Proceedings of the National Academy of Sciences, let's look at some of the claims that they make, that storms are getting more extreme, and extreme storms are happening more frequently. In their paper, Werner and Cossin suggest that at about 192 miles per hour, representing an 80% increase from Category 5 storms, a new category, Category 6, should be introduced. Werner and Cossin report of the 197 tropical cyclones that were classified as Category 5 during the 42-year period between 1980 to 2021, which comprises the period of highest quality and most consistent data. Half of them occurred in the last 17 years of that period. 5 of those storms exceeded Category 6, and all of these occurred in the last 9 years of the record. In fact, if Hurricane Patricia had been 15 to 20 miles per hour faster, this potentially would have put it in an even higher category, Category 7. An important step in their paper was clarifying previous misrepresentation of past storm intensities, particularly between 1955 and 1968, which when taken at face value show a handful of storms already over 192 miles per hour. Werner and Cossin, as well as 4 other studies they cite, explain that before modern-day approaches to satellite monitoring were available, such as the first geostationary operational environmental satellite launched in 1975, past methods were found to overestimate the wind speeds compared to what modern approaches would have recorded. And actually, after recalibrating the data of hurricane intensity, the trend looks more like this. Removing this bias presents a much starker image, with the first storm that would be categorized as a Cat 6 occurring in 2013, the Typhoon Haiyan, and several since then. But what is it that's actually driving this increase in storm intensity? There is strong correlation with sea temperature, the major driver behind hurricane formation in the first place. Let's look at historic data from sea temperatures from another source in isolation over a long period. These might look like small changes, but this is a global average. In key hurricane regions, the changes are even more extreme. In 2023, waters off the coast of Florida were measured at 38 degrees Celsius or 101 degrees Fahrenheit, which is literally, not figuratively, hot tub temperatures. Mapping sea temperatures against hurricane power dissipation index, a measure of intensity, duration, and number of hurricanes we see in a year, we clearly see very similar upward trends. Now, this isn't perfectly correlated, but definitely has remarkable levels of common features between the two processes. Cossin and Werner's main interest in their paper was a prediction of the behavior of what they refer to as extreme tail of the daily potential intensity distribution, or basically what is happening to the likelihood of forming the most extreme storms around the world, their newly proposed Category 6 hurricanes. They developed a grid-based Carnot model from the European Centre for Medium Range, or ERA5, weather forecasting data over the period from 1979 to 2019, and they made predictions for locations around the planet that typically experience hurricane formation. The figure that they produced here shows the average annual exceedance of Category 6 wind speed threshold, which broadly is a measurement of how many days did we have the right conditions to actually create a Category 6 storm. The second figure shows maybe a more clear image, the relative trend of potential intensity between 1979 and 2019 and how it changes over time. It clearly shows an upward trend in the number of days these wind speed potentials were seen in most, but not all, areas. We see significant increases in the Indian Ocean, parts of the Pacific Ocean, and major areas around the southern United States and Mexico. In their findings, they report that a 2.6 times increase in the chances of potential intensity exceeding Category 6 from the first half of the ERA5 analysis to its second half. Given that the ocean temperature is a key driver of hurricane formation, and that we've seen already that ocean temperatures appear to be rising, Cossin and Werner wanted to make predictions of the future across various levels of ocean warming. At 1.5 Celsius above pre-industrial ocean temperatures, the number of days for possible Cat 6 conditions increases up to 5 to 15 days per year in many locations. At 2 degrees Celsius, increased risk of Category 6 storms in the Gulf of Mexico increases even more, doubling in likelihood from pre-industrial levels. And at 4 degrees Celsius, we see significant global changes, on the order of 35 to 45 days per year of possible Cat 6 conditions in many places around around the world. Now, as a point of clarity and potentially minor criticism about the paper, these map days where the conditions were conducive to Cat 6 storms occurring, rather than days where Cat 6 storms did actually occur, which is then, for me at least, hard to make the jump to, well, how bad is this actually going to be? As a more intuitive example, warm temperatures don't necessarily guarantee wildfires, but on a hotter day or year, it is obviously more likely to occur than on a colder one. We are already on about 1.1 Celsius, which is why we are starting to see the first occurrences of these Category 6 level storms. And there isn't much indication that this is slowing down. Something that really highlighted the pace of this change for me was realizing that if you have a 10-year-old child, they have experienced the top 10 hottest years on record. That's a 100% hit rate. Every single year, a top 10 temperature year in history. That is wild. The question I had that remained was, how bad does this get? And that was really hard to actually find an answer to. What is it meaningful to actually say about hurricane damage if a Cat 5 hurricane is already capable of destroying your home? How do we perceive or codify the threat that a Cat 6 storm could bring? And here I'm also cognizant of overly fear-mongering, but I want to try and balance that against trying to understand what this means for us. And like I said, it's not something that's easy to come up with a quantifiable answer to, so just go with me on this slightly qualitative comparison. We do see wind speeds around the world of 200 miles per hour plus, but usually we see them in F5 tornadoes. The 2013 Moore tornado had speeds of 210 miles per hour, similar to Hurricane Patricia before landfall. Moore left behind it a path of devastation, destroying vehicles and stripping homes to their foundation. These speeds are capable of flinging 10-ton metal tanks through the air like we see here. The only maybe positive thing to say about them is that they are reasonably short-lived, lasting from a few minutes to over an hour in rare cases, and they are small in scale, typically having a narrow path of destruction that can be less than a mile to a few miles across. Giving a hurricane these wind speeds, when they can last for days, even weeks, moving across large stretches of ocean and land, with systems that can span hundreds to over 1,000 miles in diameter, magnifies their potential for widespread devastation, making each encounter a reminder of nature's unbelievably formidable power and our need to understand and respect the forces of nature that do shape our world. As for the Saffir-Simpson scale, adapting it to this new reality seems important. In some regions of Florida, building regulations require that infrastructure can survive Category 5 storms. It looks like that might not be enough anymore. Clarifying the scale and highlighting the need for even better build-outs may encourage or allow the market to then adapt relevant to these new meter sticks, though that does slightly feel like trying to bail out the Titanic with a bucket. But I think the act alone of redefining the scale is an interesting sociological question. Is this a move that helps us clarify and make visible the potential threat that is looming? Or when we inevitably don't get a Category 6 storm every single year, or when one doesn't live up to the devastating potential that we have been sold, like Hurricane Patricia because of where it made landfall, do we lull ourselves into a sense of being missold this danger, or having cried wolf too early? It's a question for the future, but my preference is to bias towards action, to invest in change we understand to be positive, and to do so sooner rather than later. If you want more global calamity, here is a video I did on dodging asteroids that are targeting Earth. If you want something a bit more fun, here is a story that I did about how we learn to see how plants can talk to each other. If you'd like to follow what I do on the days I'm not on YouTube, I'm leaving a link in the description down below to the newsletter that I run. Thank you as always for watching, and I'll see you next week. Goodbye.